So what's Chris got for us this week in issue 301? Well, what's this say? This week, why not tackle a problem originally attributed to the legendary Fermat? And there's a little picture of him, a wee caricature, very flattering. What's left over when you divide 5 to the power 999,999 by 7? So what can we do then? Well, unless you can think of a specific technique to solve a problem, the only other route would be to carry out an exhaustive investigation of the different possibilities until you either hit the solution you were looking for or some pattern that would lead to the solution, in which case you would probably go for just trying to divide the various powers of 5 by 7. Now, it wouldn't actually take that long if you used your calculator, because you could just type in 5 to the power whatever, 5 to the power 2 divided by 7, get the answer, 5 to the power 3 divided by 7. But if you were doing it by hand and doing it that way, trying each power of 5 and dividing it by 7, you'd have to go through a big list of powers of 5 like this, and then divide each by 5 by hand to find the remainder. I'm not recommending that that's the technique you should use, but maybe that's what you did in your calculator. Of course, you wouldn't have had to see these directly because it would just come up under the guide of 5 to the power. But nevertheless, these are powers of 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for good measure. And then by whatever method, by hand or calculator, you would then arrive at these remainders. You would get 5, 4, 6, 2, 3, 1. Then it goes 5 again. 4, 6, 2, 3, 1. And then you would just suppose, yes, I've got a repeating set of results here. It just keeps repeating itself every 6 times. Now that may well be true, but you've not actually got any justification in the calculation the way you did it to say that it's going to keep doing that forever. Yes, it will, but you'd have to make some sort of statement why it should. But anyway, accepting that that's the repeating set, then you can say this, right, it's repeating itself every 6 powers. So how many times would I go through this bundle of 6 in this number? So I'll divide that into that. 6 into 9, 9, 9, 9, 9, 9. We'll go 1 remainder 3. That's 6 remainder 3. So that must be a line of 6s, because I know I've always got the same remainder going on to the same number, must produce the same digit, with a final answer of 3. So it's going to go through these groups this number of times, and then 3 steps at the end. 1, 2, 3, 3 into the next group, so answer 6. The answer to this question is, the remainder is 6. There's still a question of how you got these remainders here. Those were the powers and these were the remainders. If you actually did it by hand, then that's just what you had left over at the end. But if you did in your calculator, you'd probably end up with a decimal. And if your calculator didn't have the facility to change that decimal into a fraction, you'd have to interpret that decimal by having this. If you've got 2 parts to it, if you've got a whole number part, then the decimal point, and then the decimal, if you want to find what that corresponds to as a remainder, you'd have to subtract the whole number part to leave the decimal part, and then multiply the decimal part to actually get the remainder, which is a bit tedious, as if that isn't. Better than that for 7 would be, you should know what a 7th is. A 7th as a decimal is 0.14, that's handy, it's double it. 28, that's even better, it's double that. And then it carries on 5, wait, 5, 6, no, 5, 7. Well, there's a nice little pattern I thought I had going, and then it fell apart. And that repeats itself between these 2 digits. And 2 sevenths and 3 sevenths and so on just use the same cycle of 6 digits, obviously starting a different place. 2 sevenths would start at the second biggest one, that's the 2. 3 sevenths would start at the 4. 4 sevenths would start at the 5, so it would go 5, 7, 1, 4, 2, 8. 5, 7, 1, 4, 2, 8. Which means looking at the decimal part of a division by 7, you know what the remainder should be. I'll just put it down here. That would, if it starts with a 1, it's remainder 1. That would be remainder 2, remainder 3, remainder 4, remainder 5, remainder 6. Does that ring a bell? So you might have done that, or you might have had a calculator that gave you as a fraction. And in particular, if you've got a calculator that gives you in a fraction and you've got this little button on it, so it will give you the answer as some whole number and then some number over 7, well, that number on top will be the remainder. The numerator of the fraction is the remainder you want. So you could just do power divided by 7 and read the remainder off. But then maybe whilst you were doing that, you might realise, now this remainder, now that I know it for one of them, instead of starting afresh each line and working out the new power of 5 and then dividing by 7, you could just start off with the 5 and divide it by 7, and then to get the other answers, just keep multiplying by 5. So away with that. A better technique would be then, don't get the powers of 5 and then divide by 7 to get the remainder. Divide by 7 straight away to get the remainder and work on it. Don't need a calculator for this. You would start with 5. So dividing by 7 gives you 5/7. So your first remainder is 5. I'll put it somewhere, 5. How do I get the next one? Well, instead of doing 5 times 5 and then dividing by 7, I'll keep my 5 divided by 7 and just multiply by 5. So that'll turn it into 25 over 7, which, when I bring it down from that improper fraction to a mixed number, 7 into that goes 3, would be 3 4/7. So that 4 then is my next remainder. 7 goes into the 25 3 times with 4 left over. But the thing is now, if I multiply by 5 again to get the next remainder, I'm not really interested in what the whole number part produces. That's going to save a lot of the calculation. The next remainder will just be 5 times the previous remainder. But take out these 7s if it turns out to be a number more than 7. So for my next remainder, that would turn out to be 20 over 7. Taking 7s out of that would leave you with, taking away 14, 6/7. So there's my next remainder, 6. But I know I'm dividing by 7 all the time, so there's no point mentioning that. All I need to do is work with the remainders. So instead of putting this down, there you go as well, I could just say this. Well, my first remainder must be 5 if I'm starting with power 1. And if I multiply by 5, it'll give me a 25. But take the 7s out of that to add to the whole number part. So after 5, that would become a 25, but that would change to a 4. There's a 4 left over for the fractional part. Next, multiply by 5 again. So that would give me a 20. Take out as many 7s as you can. That would be 14. That leaves you with a 6. Multiply by 5 again. That's a 30. Take out as many 7s as you can. That would be 20. That leaves you a 2. So there's the next one. Multiply by 5 again. That's a 10. Take out as many 7s as you can, that's just 1, so that's a 3. Multiply by 5 again, that's 15. Take out as many 7s as you can, that'll be 14, so that leaves 1. Now once you've hit 1, the next one would be multiply by 5 again, and obviously if you're starting with the same number and going through the same routine of multiply by 5 and then take away as many 7s, you must just repeat the same set again. That would have to be a cyclic group there. So you could say for this one, the remainders are going to form this group. I'll just put it down with what normally you see. It's not maybe the proper notation. Instead of set brackets, I'm putting the round brackets around it like a cyclic group of permutations here. And then you can say, well, if that's the group that keeps repeating itself and there's 6 in the group, then you do the same as before, divide by 6 to see how many times it goes completely through it, and then there's 3 left over, which takes you to 6. But this is very fast though. And the thing you're actually doing here each time is you're multiplying. I'll put a number line down. You're taking a number like the 25, and then you're jumping back 7s. You're taking back 7s until you end up within this range here of less than 7. There's a rubbish looking bracket. You jump back. It was like 3 you had to jump back, so that's a rubbish jump back, wherever it was. That's the process you have to do in each of them. You have to go forward to a certain number and then take off 7s till you get back into range. Now, instead of a linear number line, what you do in these repeating ones is you could take that line and bend it around into a circle. So there's my 0 there. 1, 2, 3, 4, 5, 6. And then instead of counting forward 25 and coming back, all you need to do is count forward 25, just keep going round it, and wherever you ended up, that would be the answer. Well, this used to be introduced in schools. It was called clock arithmetic, because obviously a clock goes through that process. If you go through hundreds of hours, the answers are still in the range of 0 to 23. There's another name for this arithmetic, of doing this business of instead of going along a line, you just fold the line into a big circle and keep going round it. It's called modulo arithmetic. Essentially, it's the arithmetic of remainders, what's left over. So in this case here, if it's 7s that are there, then this is a modulo 7. 7 being the modulus. So you could say what you're doing is you're carrying out, these operations you're carrying out, or these bits of arithmetic you're carrying out, are mod 7, standing for modulo 7. So you could put a wee rule down for this. What do you do to get the next remainder? If you've got a certain remainder, how do you get the next one? You multiply it by 5, and then you take mod 7. That would be the recurrence relation, if you like, the rule that takes you from one step to the next. Rn would be 5 times the previous one, mod 7. And I'm putting mod 7 like an operator there. So I've just got an equal to it. The way you could write these statements according to this counting would be this. You'd say, well, if I've got 25 and I go round this 25 steps, it would take me to 4. So that 25 effectively was just 4. Now it obviously doesn't equal 4. So what you do with this modulo arithmetic is use 3 lines. So you're not saying it's equal to it, you're saying it's equivalent to it. It's congruent to it. That's called a congruence. And you'd say according to what type of arithmetic? That's arithmetic mod 7. When you're counting in 7s, when you're taking 7s off until you get to another number. Well, that's the exhaustive examination part of it done. You the big long tedious way of actually doing the divisions and getting hold of the remainder somehow, or the quicker way of just dealing with the remainders themselves. But that's business of dealing with the remainders themselves. This modulo arithmetic. You could play about with that a bit. I'll do a wee bit here just as a diversion, because after all, back in the day of Fermat, they didn't have any tellies or Pokemons to play with. They would do stuff like this, just playing around with things, looking for patterns inside of numbers and so on. And that little theorem of his, Fermat's little theorem, that I'm going to use later on here, probably came about, although it's just a conjecture from him because he didn't prove it, came about just by playing about the same way as we're doing. So what about just a quick little play about saying, well, that was 5 to the power whatever, 5 to the power n. What about the general one? What about a to the power n divided by 7? Any number to the power n, what kind of remainders do you get? And then you would carry on further about with, what about any number to the power n divided by, and then a variety of numbers, looking for patterns. I'll go through a to the power n divided by 7. It doesn't take as long as you think, because I'm not going to be using calculators and the big long divide way. I'm just going to use remainders, modulo arithmetic. So 1 to the n. So 1 to the n, that means you'd start with a 1. That's the first power, divided by 7, so that's 1. And as soon as you get 1, it's stopped, because multiplying by 1 keeps it the same, so that set's only got 1 remainder in it. 1 to the power anything divided by 7, the remainder is always 1. What about powers of 2? What kind of remainders can you get? Well, you start with a 2. 2 7ths. Multiply by 2, you get 4. That's still under 7. Multiply by 2 again, you get 8. Now 8 modulo 7, going round the clock, takes you to 1. So that's it terminated, because 2 times 1 takes you back to 2 again. Now it will just cycle through those. What about 3? So it doesn't take that long. This is a big one. You've got 3. Multiply by 3 is 9. Go round the clock, and that will take you to 2. Multiply by 3 gives you a 6. Multiply by 3 gives you an 18. Go round the clock twice, it takes you to 4. Multiply by 3 gives you 12. Go round the clock, takes you to 5. Multiply by 3 gives you 15. Go round the clock, takes you to 1, and it terminates. As soon as you hit the 1, that's the end of it, because the next 3 times it is just going to give you the first one in that cycle again. 4 to the n, start with a 4. Times 4 is going to be 16, that's a 2. Times 4 again is 8, that's a 1, that's it terminated. 5 we did already. What was that again for the 5? It was 5, 4, 6, whoops, 2, 3, 1. 6 to the n, you'll start with a 6. Times 6 is 36, that goes round 3 times round the clock, so it's back to a 1. Now obviously 7 to the n will be a 0, because that's a multiple of 7. So that would be the set of remainder sets that you would have for divide by 7. Because after this, when you get to 8 to the n, I'll put it down anyway, because there's a wee sort of modulo rule that will come in here. Now 8 to the n would start with 8, but that's just a 1. Once you go round the clock. And 8 times 1 gives you 8 again, which mod 7 is back to a 1, so that's just a 1. 9 to the n, well 9 taking modulo 7 would be a remainder 2. Times 9 is 18, that's 4 more. 9 times 9 times 4 is 36, that's 1 more, and that's it stopped. And you've probably noticed that this pattern is just repeating again. Again there's a block of 6 here. But why are these the same as that? Well, you can do this, I'll do it with a 9. 9 to the power n you could split into 7 plus 2 to the power n. Notice the result here. In the end, since that's the same as that, you could say that 9 to the n is congruent to 2 to the n, according to the rules of mod 7. Notice the way the mod 7 goes in a bracket here, because that applies to both sides of this congruence. But surely that doesn't mean you can just, if you've got a bracket, split it up and say that's 7 to the n and 2 to the n. What that does split into, if you've done binomial expansions, would be 7 to the power n plus a whole bundle of succeeding terms where the power of 7 drops by 1 each time, until you get to the last term where its power is 0, and meanwhile this 2's been climbing up, so the very last term will be 2 to the n, and in between will be a whole bundle of terms of decreasing powers of 7 and increasing powers of 2 with other coefficients thrown in. But effectively you've just got a bundle of terms that have all got a factor of 7. Now if you're doing mod 7, then I can say this. I can say 9 to the n is congruent to that, is congruent to that, and because I'm using the congruency mod 7 here, I can say as far as mod 7 is concerned, that goes to 0 because it's a multiple of 7, that goes to 0 because it's a multiple of 7, so I'm just left with 2 to the n. That's why 9 to the n just turns out to be congruent to 2 to the n, because of all these extra terms which had multiples of 7 in it. And then, if you're back in the day, back in Fermat's day, you'd probably look, say, is there some sort of connection between these sets here? Are there any other rules hidden within there? For instance, what have they all got in common? They certainly all have got 1s. Where do these 1s occur, for instance? I've got 1, 3, 6, 3, 6, 2. Well, they all divide into 6, and there's 6 groups there. So that must mean if I continue them all, they'd all reach 1 in this column, because that would just go all 1s. I've got 2, 4, 1, 2, 4, 1, 4, 2, 1, 4, 2, 1, 6, 1, 6, 1, 6, 1, which means that then, and that applies to them, nearly all of them, any number to the power 6, when you divide it by 7, should give a remainder of 1. Or putting it in terms of modular arithmetic, A6 is congruent to 1 mod 7. That means if you start with a number a to the power 6 and go around the modulo 7 clock, you'll end up at 1 for any number, but not quite, because look, it doesn't work here. It doesn't work for multiples of 7. Make this statement. That's true so long as A7, now this in brackets means the highest common factor. As long as A and 7 have got no factors in common. If they don't have any factors in common, it's true. There's a word for that. That's called being co-prime. So long as A and 7 are co-prime, there's one rule that pops out of this. Notice that 6 is 1 less than 7. And that's how Fermat, probably, because if they tried just some other combinations, like what about different modulus, a different modulus, you know, like trying 8s and 7s and 9s and so on, would have arrived at, well, a to the power, and of course that number there, I'm going to call it p now because it only works for prime numbers. 1 less than it is congruent to 1, mod that number, so that applies in this case, so long as a and p are co-prime, as long as their greatest common factor is 1. So there you are. So this is an actual technique that you can use if you knew of this. This is Fermat's little theorem. Now I've forgotten to state explicitly that p stands for a prime number because this only works for a modulus which is prime. Well, how would you do that quickly using Fermat's little theorem? Well, you'd say this. Knowing this little rule here with these 5s and 7s, you can make straight away the statement, right, because it's base 5 there. If it's divided by 7, that'll be mod 7. 5 and 7 are co-prime, so if I take 1 off of that, 5 to the power 6 should be congruent to 1. So I've got that little statement to work with. Now I've just got to modify this. So I'd start with this and say, maybe I'll go slightly further over. I'll say, well, 5 to the 999,999. I'll just use congruent here, even though this thing's going to be identical, although it's still strictly speaking correct, is the same as 5 to the power 6, all to the power, then divide that into that. I've already had that number, 166,666, plus another 3, so times 5 to the power 3. This part is congruent to 1, and 1 to any power is just 1, so all left was 5 to the 3, and 5 to the 3 is 125. And then manually just finding the remainder after you extract 7s from that, would be 1, remainder 5, 7, remainder 6. It's congruent to 6, whoops, not let myself room there, mod 7. Answer is, the remainder equals 6. Don't go away yet. There's one more way that could have been done. Going back to that binomial part at the beginning, you could take this power of 5 here, and rewrite that 5 as a 7 minus 2. So you've got 7 minus 2 to the power 999,999. Then realising that you're going to have, remember it's always one more, there's going to be a million terms here. So that'll be equal to 7 to the 999,999 plus all these terms, almost a million of them, going all the way down to this negative 2 at the end, which has gradually been creeping its way up until it's reached 999,999. And in the middle, you've got that big, huge pile of terms, but they all involve 7s. So that would be equal to that. So upon dividing by 7, that would have no remainder, that would have no remainder, so effectively it boils down to what's the remainder for this thing. So if I just use the language of congruences again, of modular arithmetic, I could say this. 5,999,999 boils down to, now that's an odd power, so it'll be negative of 2 to the power 999,999. Now that 2, I'm really looking for 7s here. 2 to the power 3 is 8. So if I change that to, and this negative's a bit of a nuisance, 2 to the power 3, and then that would all be to the power 333, 333. It's equivalent to that, which is of course 8. This is all for, I don't actually need to do this in mod 7, these statements, well those statements aren't true, unless I'm dealing with mod 7. Then, that 8, so now I've got 8, so I could break that into negative, I'll just continue over here, negative, and the 8 can be broken into 7 plus 1 to the power 333, 333, you see where that's heading now, same as before, that'll split into 7 to the power 333, 333, plus a whole pile of terms that involve 7s, and the last term, the 1s crept all the way up to 1 to the 333, 333. And the handy thing, I suppose, about keeping the mod 7 going is that'll disappear because it's a multiple of 7. That'll disappear. They'll all disappear because it's a multiple of 7. And that's just 1. So I've actually ended up with negative 1 mod 7, which seems a bit naughty because it's a negative number. But in terms of remainders, A negative remainder really means 1 before a complete bundle, and 1 before a complete bundle is 6 after the previous complete bundle. Or if you just think of the modulo 7 clock, negative 1 means going backwards 1, which takes you to 6. So that actually makes 6 mod 7. So there's another way you could have done it, with a binomial expansion. Well, actually with 2 binomial expansions. Well, that took quite a bit this time. Not like that previous puzzle.